Welcome to my new calculus channel. I am John Gabriel, and in this video I'll be talking about a very controversial subject, the topic of 0.999 and whether it does in fact equal to 1 or doesn't equal to 1. Well, first of all, let's get right to the point. It's a fallacy, and it has its origins in Euler's or Euler's wrong ideas. The only support for this fallacy comes from Euler's definition of infinite sum, which is both illogical and spurious. And what Euler did was, basically, is he said that if you have a sequence such as 0.3, 0.33, 0.333, ... then let that sequence be A, like that. Then the limit as n approaches infinity of the sequence is equal to 1/3, and he defined that to be 0.333 ... Well, there are a lot of problems with that. The first problem that comes to mind is the fact that 1/3 is not measurable in base 10, is not measurable in base 10. What does that mean? That means that you can't find an equivalent fraction in base 10. For example, if you have a quarter, that's the same as saying 2/10 plus 5/100, which is 25/100, or 0.25. So there is no way you can do this with a third. You cannot write 333 over 1,000 plus ... Okay, somebody else might retort, in fact I was the one to do this initially, might retort as follows: 1/3 is equal to the sum k equals 1 to n of 3 over 10 to the n plus 1/3 times 1 over 10 to the n. Well, this is always true, but there's only one problem here. If we, for example, say 1/3 is equal to 0.33, like that, plus 1/3 times 1 over 100, that's the same as saying 33 over 100 plus 1 over 300. Now remember what I said about it being equivalent to a fraction in base 10? Well, the denominator has to be a power, an integral power of 10. This denominator here is not going to be an integral power of 10. In fact, it turns out to be 300, right? And 300 is not an integral power of 10. So for example, there we have 10 squared, but here we have 3 times 10 squared. So there is a theorem, a number theorem, which states that in order for a fraction p over q to be measurable, or to have an equivalent fraction in a radix b, then b must contain all the prime factors of q. B must contain all the prime factors of q. Well, it's clearly evident that 3 is not a prime factor of 10. Therefore, 1/3 cannot be measurable in base 10, and there is no equivalent fraction. And of course, this here is nonsense. I'll tell you who came up with this initially. There was a Dutch arithmetician whose name was Simon Steven. And Simon Steven wrote a book, the very first book, on non-terminating decimals. So the reason Steven wrote that book was so that people didn't have to learn very much about fractions. In fact, the idea was that you have a radix system where you have the radix there and the different columns like that. Yes. And then you'd be able to represent a rational number in that radix system in a unique way. By the way, it was unique, and and so you could use this radix system here or any other radix system to represent given numbers. So if you had a quarter, well, you would need 2/10 and 5/100, 25/100, right, or 0.25. If you were to carry a template around with you like that, you wouldn't even need 0 in mathematics, because all you would do is put a 2 and a 5 under the respective columns, and you could just leave everything else here blank. You wouldn't even need this 0. But of course, if you just wrote 25 like that, it could mean just about anything. It could mean 0.25, it could mean 2.5, it could mean 2,5 million, it could mean 25,000. So the zeros are for human consumption only. Okay, so this is basically how the radix system was designed. Steven put together certain types of rules. So you could actually add decimals and multiply them and subtract them and do lots of other things. So for example, if you were to add those two decimals, then you would simply add what's in the column. If there's a carry, you would perform the carry. Otherwise, you would just carry on adding. So somebody could learn how to do this and not understand anything about the fact that 3.51 is the same as 3 plus 51 over 100, which is the same as 351 over 100. They wouldn't have to know any of this fractional theory. Similarly for 23 and 3.74. So this radix system was designed so that the average Joe could do the basic operations of arithmetic, which are multiplication, division, subtraction, and addition. Okay? So that was the reason Steven came up with the book he wrote on decimals. It's possible to have any other system you like as well. So for example, but before we go to another system, let's just take a look at how we would convert, let's say, a quarter into base 10. Well, most people would say 4 divides 1. Nope. So put a 0, and then don't add a 0. You multiply by 10. 4 divides 10 2 times. Remainder what? 2. Yes. Multiply by 10 again, and 0.25. Yeah. That's actually just the fast way of doing it. But the correct way to do it would be to say a quarter multiplied by 10 over 10, which is the same as 10 over 4 multiplied by 1 over 10, right? Which gives us 2 plus a half times 1 over 10, which is the same as 2 times 1 over 10 plus a half times 1 over 10 times 10 over 10, which gives us 2 times 1 over 10 plus 10 over 2 times 1 over 100, which gives us 2 times 1 over 10 plus 5 times 1 over 100. And those are the significant digits that go into our radix. Okay, so this would be 10 to the 0, this would be 1 over 10, 1 over 10 squared, this would be 10 to the 1, etc. And so here we go, placing the 2, 5 there, and we're done. So we've actually found an equivalent fraction in base 10. If you were to try this process with another base, you'd follow exactly the same procedure. So for example, if you wanted to see what is a quarter in base 7, then you would say a quarter times 7 over 7. And that would be 7 over 4 times 1/7, which is the same as 1 plus 3/4 times 1/7, which gives us 1 times 1/7 plus 3/4 times 1/7 times 7 over 7. And again, you'd have that. Okay, and that would give us 1 times 1 over 7 plus 5 plus 1/4 times 1 over 7 squared. So it seems that you could continue this pattern in base 7 by saying that a quarter is equal to 0.1515 recurring in base 7. Of course, this here doesn't really happen in reality. It's just a symptom of trying to convert a particular number into a base that doesn't have that as a prime factor. 4 is not a prime factor of 7, so whatever you get there will not be a finite representation. It will always be a non-terminating representation. Now, as you know, non-terminating representations depend on the concept of infinity being valid. Infinity is not a valid concept. Okay, so this here is nonsense. Of course, you can do fancy things if you decide. For example, let's take a look at this. If, for example, you say, well, a quarter is equal to 0.15 recurring in base 7, that's the same as writing two series like this. 1 over 7 plus 1 over 7 cubed plus 1 over 7 to the 5, yes, plus 5 over 7 squared plus 5 over 7 4 plus 5 over 7 6. And you could take the limit of each of these series, and the limit of this one would be 1 over 7, and then it would be 1 minus 1 over 49, and that would give us 1 over 7, and we'd have 48 over 49. Multiply both sides, multiply both top and bottom by 49, and we'd have 7 over 48 here. Similarly, on this side here, we'd have 5 sevenths. 1 minus 1 over 49, that's going to give us 5 sevenths over 48, 49, which will give us, if we multiply both top and bottom by 7, we're going to have, by 49, we're going to have 35 here, aren't we? Is that correct? Oops, that's actually not 5, that's 7 squared, I'm sorry. So that's 49 there. So if you multiply both top and bottom by 49, we will have 5 over 48, yes? So now if we add these two again, which are the limits, we'll get 12 over 48, and we see that 12 over 48 is the same as a quarter. So it would seem that this here justifies writing a quarter in base 7 as a non-terminating representation. In fact, it doesn't justify it because we're looking at limits here. A quarter is not measurable in base 7. In other words, there is no equivalent fraction in base 7. There is no way you can write a quarter in base 7 with an integral power of 7 like that and something on the top here. Right? That's what it means to find an equivalent fraction. So, let's go back to, let's first of all clear this. I don't want to say that. Let's go back to my document here. So now, what we have here is Euler, who believed that 1 divided by infinity is equal to 0. Well, you know, up till this day, most academics don't even understand what a fraction means. If I had to tell you if I had to ask you what does P over Q mean, where P and Q are integers, the best answer you could give me is to tell me that Q is the number of parts, equal parts, that the unit has been divided into. So if we add up all these parts here, they should add up to Q. Okay, that's what the bottom part means. That's what denominator means. And so let's see how this scheme works with 3/4. What does that mean? It means the unit has been divided into 4 equal parts, and we are only interested in 3 of them. 1, 2, 3. Okay. So naturally, if you write something really stupid like 1 over infinity, or k over infinity, some number over infinity, what you're saying is you've divided the unit up into infinitely many equal parts. What is this? It's absolute nonsense, okay? So there's no way to do this. For the very same reason, you can't say k divided by 0, because that means you've divided the unit up into 0 equal parts. That means 0 times some number f has to give us 1. That's absolutely impossible, because 0 times any number will be 0. So obviously Euler was on the wrong track, and these ideas permeated mathematics, and we had George Cantor, who came along and made matters a lot worse. And so things progressed to the point where modern academics just went from bad to worse. And so today we have this wretched concept where students are told that 0.999 is equal to 1, 0.999 repeating is equal to 1, and of course nobody ever believes it at first sight, and many never believe it for good reason. This document that you're looking at right now, proof that 0.9999 is not equal to 1, is going to be available at my YouTube channel, so you can look at the whole document. It's about 49 pages long, debunks every proof in favor of the fallacy, and shows that no matter which approach mainstream mathematics tries to justify the belief that 0.999 and 1 are the same, all the proofs are false, and they've been invalidated in this document. In fact, I will also provide the link to another document, which is called page 317. There's a good reason it's called that. Page 317 is the discussion that has taken place on space-time in the universe on page 317 in that forum. And this document here debunks the misconception that Dedekind cuts and Cauchy sequences are valid constructions. They're not. And in this document I prove, using mainstream methods and the definitions that were handed down by Dedekind and Cauchy, that both the constructions are invalid. I'm not the only one who's of this opinion. I know at least 5 or 6 other mathematics professors who agree with me. And so I'm definitely in the minority, but I'd rather be in the minority than counted among fools. And I'd rather publish truth and be unpopular than basically just move along with a lot of sheep who are simply regurgitating what they are told. Now, in this document here, I really summarize what mainstream academics do. Well, what they have really is that the number is the limit of a particular sequence, and in the case of a quarter, the limit is the sum. So let's call that rule 1. In the case of a third, the limit is not the sum. So I showed you 2 examples here. What I did was I showed you how when you write a quarter, in base 10, oh dear, when you write a quarter in base 10, you have 2 tenths plus 5 hundredths, okay, and it's final. Yes, it is the sum. So if we add those 2, that's actually a quarter. But a third is never the sum. Okay, doesn't matter how many you write. You can't have infinitely many because there is no such thing. So you could write 333 over 1,000 plus, but that's not an equivalent fraction. So in this case here, a third is equal to the limit of this sequence. Okay, limit of sequence. In this case, a quarter is equal to the sum. So a third is equal to the limit of the sequence, and a quarter is actually equal to the sum. And then finally, rule 3 is the case of special magnitudes, incommensurable magnitudes such as pi and square root 2. No one has a clue what the limit is, except that its sum symbol or its partial sums can be approximated by some formula. Rule 3 is particularly amusing because it assumes the completed infinite radix representation is possible. Mathematicians define the number by this myth. Interesting to note is that if one accepted the infinite unique representation, then whatever is a limit, it is not equal to the completed infinite representation. Well, there is no such thing. Because if it were, then guess what? All irrational numbers would be rational, and that makes no sense at all. This document is a very damning document. Most mainstream academics do not like it because it's filled with facts that they can't refute. And I will provide a link to this document also when I upload the video, the YouTube video. So far we've actually looked at some proofs. This main document here has a lot of proofs that are debunked. It even explains what is the long division algorithm. There is a misconception that we get this non-terminating radix through long division. That is untrue. Long division has nothing to do with this. In fact, long division is a finite algorithm. Okay, so whoever came up with this idea first was an idiot, in very simple terms. No long division is taking place here. Some other interesting facts are that people think that when you write 1 over 3 like that, that the vinculum means division. In this case here, it doesn't mean division, and no division is taking place. The division has already taken place. The only time the vinculum means division is if the numerator is greater than the denominator. Then you have 1 plus a third. Then it's the same as the obelus. This here is called the obelus. Okay? So only in this case is the vinculum the same as obelus. But this division process is a finite algorithm. All these details are described in my documents, in these articles that I will provide links to on the YouTube channel. And finally, here's another very damning applet that I like to show to people. This here is the function of 1/3, and it shows us what happens as we basically move towards greater numbers like that. So we can put in 10 there, and that would be the result. Now, if you theoretically could go to infinity, you wouldn't have a value there because infinity cannot be reached. If you look at these graphs here, the red graph, which is the graph of this function, is asymptotic to the blue line, which is actually equal to 1/3. The blue line here is 1/3. They never touch. Thus, if 1/3 was truly equal to 0.333, then theoretically this graph should touch the asymptote. But then it wouldn't be an asymptote, would it? It's called an asymptote for a good reason. They don't touch. Mathematicians just seem to, not mathematicians, mathematicians just seem to lose all reason when it comes to plain facts like this. I really can't understand that. It's quite a frustrating concept trying to explain this to them. But there are people who do get it. And so this document here, back to the main 0.99 proof document, it has everything you need to know. It refutes the common 10x proof, which is kind of funny because the 10x proof is really a proof that they're not equal. Let's see if I can find that very quickly. So if we go down here, there are lots of proofs in here that are very, very, very solid. Okay, so let's look at this first one here. So this first proof here is hilarious because the algorithm that is used is a fallacious argument. If we submit an object R to this algorithm, we must get R out. Yes, by definition of the algorithm. Now, if for some unknown reason you get something different out, well, then you should ask yourself, why is the input not the same as the output? Perhaps you've done something wrong in your calculation, right? So if an algorithm produces results contrary to its definition, it should be looked at very suspiciously. Don't you agree? It does not take an imbecile more than 10 seconds to realize that if the algebra is valid, which it is, then perhaps something is wrong with the input that produces two apparently different results. Now, you know, my guess is that there is a lot that is flawed with the thinking of modern academics. The answer is that one obtains absurd results when mixing numbers with the concept of limit, because a limit is sometimes a number and sometimes it is an indeterminate ethereal concept. So if we go back to this document here, I'll show you right at the end the three rules. In this case here, it's an ethereal concept. Nobody knows what it is. Mathematicians like to say it's the infinite radix representation in whatever base you're representing it. But that's absolute rubbish, because even if you could sit down and write the radix representation of such a number, and you could live forever, you would never finish. And in fact, it doesn't matter how long you lived, you'd still be, quote, infinitely far away from completing the process. Thus, that kind of definition of number is idiotic, totally idiotic, and does not belong to mathematics. Okay, so that's the main 10x proof, which is debunked. Another really funny argument is that, but can we find a number between 0.999 and 1? Well, that argument is invalid, because you'd first have to establish that 0.999 is a number. Well, you can't do that. You can't even establish that 0.999 is a point on the number line. Okay, if you look at the interval 0, 1 and the interval 0, 1 like that, this is a half-open interval. It doesn't have an endpoint here. Okay, so you might be tempted to think that that represents 0.999. It actually doesn't, because this sequence here never terminates. It has no last 9. And then you can look at it and say, well, 0, 1 has two endpoints, so the length or the measure of this segment, the measure of that must be 1. But nobody knows what the measure of this is. Even though theoretically it's supposed to be 1, it doesn't have a measure. It only has one endpoint, 0. 1 is not part of this interval. So there are a lot of proofs that are not really proofs, but misarguments, or rather fallacious arguments, which don't really count. Now, this document here that you're looking at has a lot of other proofs inside it, and a lot of other knowledge that you probably have never seen in your life before. Some of it is a little outdated, and I've actually changed my ideas on some things, but not drastically. It doesn't really alter anything as far as the argument goes. I would recommend that you read it and study it carefully, because it makes a big difference when you're learning mathematics and you want to understand why things are the way they are. So, to summarize this whole video, 0.999 is not equal to 1, and 0.333 recurring is also not equal to a third. You've been watching the New Calculus channel with John Gabriel. That's all I have for now. Take care. I hope you'll join me next time. Bye-bye.